good afternoon. My name is Flavia, and I'm a PhD student at the University of Reading, and being supervised by Pitian Van Leeuwen, and also working with Ulrich Palitz. And well, this work is funded by Science Without Borders program in Brazil, Brazilian Navy, and also National Center for Earth Observation and the European Research Council. So today I'm going to share with you some results I've got with this work on synchronization for data simulation. Synchronization was first observed very early by a Dutch scientist, and well, he had these two pendulum clocks here, and with a frame, and these pendulum clocks, they were oscillating, and he observed that after some time, independently on the initial conditions, these pendulum clocks started to oscillate in opposite directions, but with same frequencies. And he observed further that if an intervention was made in one of these pendulum clocks, after some time, they started oscillating again in opposite directions with same frequencies. So he has attributed this sympathy of these two clocks to the frame they were sharing. And well, I'll try. Yeah. So he has attributed this sympathy to the frame they were sharing and its motion as well. That is, it's like a coupling factor. And so the main idea of the synchronization is that if two or more systems share or exchange information, useful information in the correct way, they can synchronize. So data simulation aims something similar, aims to synchronize the model with the true via the observations. And these observations, this coupling is unidirectional, and these observations are sparse, and they have errors. We all know that. So some researchers have tried to find the equivalence between these concepts of synchronization and data simulation, like Duran et al. Some others have started to work with time, the concept of time embeddings, time delays, like, for example, Barbanel, and also Ray et al. Particularly these guys here, they've achieved some remarkable results on trying to synchronize systems. And they were using Lorentz-96 model with 20 variables, and just one was observed. And they were trying to vary these time embeddings. And it's a very crucial factor, these time embeddings, because you need to have, you can use information either from the past or from the future to bring additional information to the present time. So these guys are trying to vary the size of these time embeddings until they've reached RMSE values of around 10 to minus 15, which is machine precision. This is really remarkable and significant. But it's not so realistic because they were not using observation errors, and also their framework used the propagation of a sensitivity matrix, which had the size of the dimension of the system. So this is really costful. So our work here, we're trying to deal with high dimensional nonlinear data simulation, and our aim is to work with particle filters. But we know that basic particle filters, they do not work so well in many cases, and we're counting on the proposal density freedom. So we believe that synchronization could be a potential choice as a relaxation term into a particle filter. So all this work here, I'm not showing results for particle filters. I'm showing results to try to find an efficient scheme to be a relaxation term into the particle filter. So the synchronization framework Ray et al. Were using was based on this variable evolution here. So we have a nonlinear model. They use a coupling constant Gn, which in our case here we can consider as 1. It's a tuning parameter for that case, but for us it can be considered 1. And we've got this pseudo-inverse here. It's a pseudo-inverse of a Jacobian matrix, which can be considered as the frame, that these two pendulum clocks here are sharing. So this is the state vector, on the observation vector, and this is the state vector. Both of them are constructed into this concept of time embeddings. I'll show you later. So this pseudo-inverse here is the responsible to spread information from the observed variables to the unobserved variables. And these two vectors here, they are constructed in these time embedding concepts in which we get information from the present time plus tau, in which tau is a time constant. In this case here, we're using 10 time steps. And we go through ahead and bring this additional information so far as we need. The state vector is also constructed in the same way as H is the observation operator. Note that both vectors have this size, dE, which is the size of this in time embedding, and dy, which is the number of measurements we got. Notice there's a similarity between this and the ensemble smoother and a common smoother. So the Jacobian matrix is of size d times dy, which is the number of measurements, by dx, which is the size of the system, the size of our system. And then we calculate the pseudo-inverse of this Jacobian matrix through an SVD. And there's an issue here, because for us to construct this Jacobian matrix, we need to propagate a dx by dx matrix. And if we are dealing with a high-dimensional system, this would be very expensive. So the solution we tried to develop was to construct this Jacobian through an ensemble approximation, and then this could be hopefully very much cheaper. So this is our framework. It's kind of simple because we generate an ensemble of phi initial states. We form an initial ensemble perturbation matrix, which is each ensemble minus the mean. And note that this ensemble perturbation matrix here is a dx by NN's matrix, which NN's is the number of ensemble members we're using. And I'll show you later that I'm using a small number of ensemble members. And we propagate this ensemble perturbation matrix forward in time for tau time steps, the same tau they use in the synchronization framework with the matrix propagation. Obviously, this matrix has the same dimensions as the previous one, and we also generate this augmented d times dy dimensional vectors here, y and s. This time, S is constructed by the states being the mean, the ensemble mean, at each embedding time. So now my Jacobian matrix is a d times dy by NN's, and not the size, and not dx, which was the size of the system. So this is much smaller than the previous matrix I was presenting. And after some maths, for us to calculate the pseudo-inverse of this Jacobian matrix, I just multiply the initial ensemble perturbation matrix by the pseudo-inverse of this, the perturbation matrix which is propagated tau times ahead. So now in this case, the pseudo-inverse is calculated on a dE times dy by NN's. And the computational gain we've got here is very promising. So I'm showing some experiments we've done with the synchronization using matrix propagation, like Ray et al. Have done, but specific in our case, we've added observation noise, and I'll show you the difference with this detail, and also results for our ensemble-based synchronization. So we're doing performing twin experiments with the Lorentz 96 as well, with 20, 100, and 1,000 variables. So this is the equation for Lorentz 96, for those of you who still don't know. And we are observing 25% of the system. In that case, they were observing just one. But you see that as I'm including observation noise, now I need to observe better and more the system. The observations are equally distributed on the Lorentz ring. And as I've said, now we are adding an observation noise. So for the synchronization using matrix propagation, these are the values of the trajectories of an observed variable and for an unobserved variable for a 20 variable case, simplest one. And the blue lines are the truth, and the green lines are our estimates or predictions. So our estimation period goes until 10,000 time steps, and after that, it starts our prediction period. So what we can see is that our during the estimation period, you just can't see the green lines, hopefully. And this is good because our they go on top of each other. Our estimates practically match the truth. And for the prediction period, what we see is that after around 500 time steps, our predictions start to diverge due to the fact that the model is chaotic. This is for the observed variable, and for the variable that we don't have any observations, we've got the same situation, same behavior. We practically perfectly estimate or match with the truth. We don't see the green lines, and around 500 type steps later, we start to diverge. So quantitatively, how are the results for that? So these are for different sizes of time embeddings from 2 to 5, and the RMSE values in a log scale for along the time run. So what we can see here is that, well, as I've said, the size of the time embed is a crucial factor because it needs to be long enough to bring this additional information we need due to the lack of the measurements, but it needs to be small enough not to generate instabilities on the computation of the pseudo-inverse. So what we can see here is that for d equals 2, it's too small for us to get enough information, additional information for the system to spread from the observed to the unobserved variables. But for d equals 3, 4, and 5, we can see values of RMSEs of around 10 to minus 2 or 10 to minus 3, around 10 to minus 2, 10 to minus 3. What we know is that it's not 10 to minus 15, like the previous one, but we have included observation noise. So this is really practically related to that. And so this is the result for synchronization using the matrix propagation. So how are our results with the ensemble-based? So they're quite similar. For d equals 2, this is not enough yet. For d equals 3, in our case, we can see some moments of desynchronization. And I can say here that values below 10 to minus 1, we are considering very good results, significant results, because it's below the observation noise we are adding. So for d equals 3, in our case, it's still not enough. And for d equals 4 and 5, we still get synchronized and stabilized results here. So this is for 20 variables. We are applying localization, and we are using only 5 members for that. So what happens if I increase the size of the system? So if I increase to 100 and 1,000 variables, this is for 100 and for 1,000. Again, localization is applied, and for 100, I'm still using 5 ensemble members. For 1,000 variables, I'm using 20. I had to increase to 20 ensemble members. And again, we have stabilized and synchronized results of the order of 10 to minus 2 for RMSEs, also of the order of 10 to minus 2 for 1,000 variables. And it's interesting to note that some preliminary tests with 10,000 variables show that, well, until here, the synchronization using matrix propagation is a bit faster than our ensemble case. But if we try for 10,000 variables, the ensemble-based synchronization starts to get 4 times faster, and I think this will increase as I increase the size of the dimension. So as a conclusion, well, the same now to compare. These are trajectories for the 1,000 variables. These are 2 unobserved variables. And again, we estimate very, very precisely, and our prediction range has reduced a bit to around 300 time steps, but yeah, we still can get very, very significant results for these. So the conclusions that, well, the synchronization using matrix propagation have slightly better RMSE values, as I don't know if you have noted. They were around 10 to minus 2, 10 to minus 3. In our case, it was around 10 to minus 2. But they cannot be extended to high-dimensional systems. As I see now, running for 10,000 dimension system, it's really slow. Our ensemble-based synchronization works well for desirable small number of ensemble members, and it is promising. So now we're trying to implement this in a particle filter as part of a relaxation term, and hopefully it can help the nonlinear data simulation. Well, thanks for listening.